Horrifying example and some yeah, but I don't think I'm gonna find anything. Normalization. So normalization, wave function. 3D space. Oh, okay. Look at this. Maybe normalization of wave function in 1D and 3D. Maybe that helps actually. That is.
Now, one of the most important thing is how we're going to be able to discover particles in a specific space, drawn as this over here, where we have a particular curve over here, and we're going to target this particular region where position is labeled as X, however, at the region. Now, the probability of finding our particle become function was connected into that side. We have our wave function that acts on the X, Y, Z, or T. This is for all space over there.
Yeah.
Now, let's look at how we'll be able to start the normalization process over here. Now, for normalization, the probability of finding a particle in a region which is dx, in this case, in one dimension, is actually equal to the product of normalized constant multiplied by a complex conjugate, alongside the normalized constant multiplied by our wave function, all with respect to dx, since we are all involved, or this is applied to a one-dimensional system. Now, the sum of the individual probabilities must be equal to 1. So, mathematically speaking, what we are trying to say is that.
So probably he's gonna do the 3 dimensions separately
probability over here,
and add them,
which is the square of your wave function. Your square of the wave function must be equal to the normalization of your complex conjugate multiplied by
yeah.
of your team chance to grow and can be put at complex conjugate.
Okay, that's so we've done this.
And the integral. Or on the other side, if you're writing it in our 3-dimensional system, is written as this long event. In quantum mechanics, complex conjugate and the wave function is equal to 2x, or square root over there.
Yeah.
So the n will be determined in order to normalize normalize event function. All these.
Okay, so it does. So it's just.
3-dimensional system over here. Now this particular segment or coordinates over here are all equal to tau over there. And once you're able to solve this for our 3 dimension, then you can be able to apply that for 3 dimensions, while on the other side,
okay. I mean, yeah. Why not? We could try it. I mean, I don't know if I thought I had tried that in the past. Instead of just playing with polar coordinates and whatnot, I thought I had tried that in the past. I mean, I assumed in 3D space, this distance is like the distance. It's just the square root of, and then yeah, exactly. So that's the origin. So it's this thing here. Okay, so that's R basically. I mean, yeah, why not? We can try that. And so we can do these basically Cartesian. And so basically, you know, our S1 is, so this is basically square root of x squared plus y squared plus z squared. Okay, so here we actually define basically, let's see, let's just define these things again. NA, we don't define R and all these thetas and stuff like that. So we just define, can we do X, Y, Z, and then define X, Y, Z? I think you can do these. They're real and they're real, but they don't have to be positive. So I hope that is, yeah. And then what we're doing is we're integrating from minus infinite to plus infinite. And so we're yeah, okay, but the thing is probably this is, I don't know. So this guy just literally does this like that. Yeah. And so basically what we're doing is S1. So S1 is the integration of S01. And then first we do X and we do minus infinite to infinite. Okay. What the fuck is shouting like this, man? Then we do first X and Y then Z, for example. Right? So, I mean, you know, that would have been quite stupid. If that works out, then this is Y. The thing is, this might just be complicated. 3, and this is Z. Now S1, S1, and then S2, and then S3. So once I have everything, then I solve for. Then we solve for, you know, this and then times n and the conjugate of n minus 1, so that we print S4. Will that work out? I don't know. At this point, I'm already just desperate enough that Python exercise 2. This might just well take a long time. What is these? Or do I just define them separately? Maybe. Although I'm sure that does not necessarily have, or you know, the solution is really elegant because it has this pi. I forgot almost. I think I must have tried that at some point. Yeah, fuck it. I must have tried that at some point. The thing is, I don't know why it doesn't work. I don't know why it doesn't work, but actually now I realize the reason I abandoned that idea is because of pi being in the solution, which kind of I was like, where do they even take that from? And so I'm basically stuck at the same same step. I'm very stuck at the same step. What have we tried? We've tried 2D space. We've tried 2D space, and that almost gives me what I want. Because the solution is and again I'll probably have like 10 more minutes. I just wanted to try this one because I thought maybe I hadn't tried that before, but I did have, I think. Shit. The solution is this. Ugh. A T0. I'm sure it's I'm sure it should be this, but then this also doesn't give me exactly what I want. What's more, it's kind of even worse in a way. It's like, what are the boundaries? And there's constants in the middle. R is definitely bounded from 0 to infinite. Cylindrical okay, so cylindrical coordinates. Okay, well that's just cylindrical coordinates, right? No, n-dimensional cylindrical coordinates. On numerical integration routine, especially in finding narrow peaks in smooth integrants, this works based on multiple instances of Monte Carlo. Normalized function. I'm constructing a normalized function R3 to R, which peaks in Cartesian polar and cylindrical coordinates. It consists of lengths and peaks, not normalized as they cannot be normalized in higher dimensions. For radial components, different coordinates. What the hell? Question. For n dimensions, n terms with Lorentzians, but I also need n-dimensional cylindrical coordinates in 3D. Okay, so is there anything, that's what I'm interested in, generalized cylindrical coordinates for n dimensions? Is it possible to just use spherical coordinates in n dimensions and just attach n orthogonal Cartesian coordinates to it, like in 4D? That seems to be like something that I should maybe try to understand. It's super useful from an abstract perspective, but I'm also like, it's too much time. Would it be a valid coordinate system? Is this, Great, there's no answer. Ooh. How do you mean, would this be a valid coordinate system? This almost seems like too crazy for that exercise. That's my problem. To this space is so much more comfortable and it makes so much more sense, but it doesn't give me the solution that I want. It tells me just spherical, cylindrical integration. What's more, cylindrical integration would be even easier, right? In 2D, because then you're saying it's R. So you start with integrating R that goes from 0 to S1. No, you integrate Z, sorry. Then you integrate R. And what was that giving me? Yeah, I have to go. Ah, that's far from optimal, far from good, actually. Spherical coordinates. Yeah, it's a cool picture, I think. Khan Academy. So this is basically the volume of this. Yeah. And so essentially the saying is like R squared times sinus of phi. Yeah. That's why R squared times sinus times this. And so this is what you would do. The R, the theta, and this theta is what finally here in this picture is this, because the other one is psi, correct? Yeah, psi. Oh no. This guy, the long shit, is this one, and we first do this. First do R, this. So if we do it this way, then it's okay. Phi and theta. Okay, so phi, and so here we do the function times this. We do the radius, then we do phi. And yeah, that actually is, it's not phi halves, it's really phi, right? Okay, because I know that it can be, I can, yeah, that is phi divided by 2, because you just go, because you know that you're not going to get negative values. Z is never going to have negative values, and so you do these, and then 2 pi for theta. Yeah, that's what it seems like it should be, but that's what's giving me this crap. And if I, oh no, that's giving me a better result. Okay, yes, sorry, that's giving me a good result. I mean, if I, the thing is, if I do that, then I'm gonna get something bigger than that. Okay, but look, I'm not getting the coefficient, so that's actually better in a way. Almost there somehow. Almost there. Or isn't it the... So, where's the thing here? So this is... am I stupid? Where am I? Almost there. It's kind of almost there. A positive true. If we don't say... what happens if we change some of these preconditions? And I'll have to drop, guys. I'm sorry. Does it change anything? Okay. Okay. Okay, there's something there. There's something there. There's definitely something there. Yeah, man, I don't know. It sucks with that. There's a lot of stuff missing here, but anyway. Anyway, see you next time.